Alright, so we're starting with number 9 here. We've got the train car moving at this, collides and connects. The train car of equal mass moving in the same direction at this. Ooh, if they connect, what type of collision is it? Not only inelastic, but also perfectly inelastic. So, since it's a perfectly inelastic collision, I'm going to actually write that in here just to remind myself that's too big of a font. Do that in 24, that's better. So perfectly inelastic collision. The impulses are equal and opposite between the cars. Alright, because I remember on my rubric I want to make sure that I talk something about it. Impulse is shown incorrect in diagram or mentioned. So in this one that kind of hits that criteria. Now, let's draw. So, I've got the first card and the second card. Momentum 2 before, momentum 1 before. Actually, you know what? I'm going to leave off the book. We'll leave it. And then what happens after they hit? Because it's perfectly inelastic, they become one object. One object. So afterwards, we've got this single big object, and it's going to have, and I'll call that momentum 1, 2, and I'm going to put an A on that just for after. Let's see. Clear understanding physics is a problem. Yep. Now I could always add up here that if I was worried that, okay, am I really showing that I clearly understand the problem? I could always add in here, that momentum is conserved, but kinetic energy is not. If I was concerned that the reader wouldn't understand that. Clearly the problem, sketch a roadmap to the how. I think so. All momentum shown in correct in diagram. Yep. Yay. I think I got it. Good. All right. Let's go down to our how then. Extend our page a little bit here. And so let's grab some physics equations. And I need my equation. I know I need my equation for momentum. I'm going to put that in there. I think that's all we need. So I'm going to actually start with the equation that my diagrams show me. That beforehand I have those two momentums and they're both in the same direction. I knew that because in the problem they told me that they're moving this way, collides and connects with the car of equal mass moving in the same direction. So I knew these two are in the same direction, and then I know that the momentum before equals the momentum after. So which direction do you guys want to call as positive? To the right? Everyone agree with that? Okay. So let's call it to the right positive. So my equation that I'm going to write down here is that the momentum 1 before, the vector, plus the momentum of 2 before, as a vector, equals the momentum of the combined 1 and 2 afterwards. That's direct. That's why I did the diagram, so I know how to start. So that's my direct connection between the two. Now we'll just substitute in using our equation here. So this would be the mass of 1, the velocity of 1, plus the mass of 2, velocity of 2, equals mass 1 plus mass 2, because they're now combined into a single body, and the velocity of 1, 2. Now I dropped the B and the A because it's not like I have object 1 before and object 1 after. I can leave them there if you want. Alright. So now it's really just filling in, right? Let's see. M1, 25,000 kilograms. Velocity, 2.5 meters per second. Plus mass 2 equal mass. Excellent. 25,000 kilograms minus moving at 1.00 meters per second. In our room again. A little math in my head. Making sure what there. Oh, okay. I didn't even see a second part. I'm going to have to go back and modify a little bit. And I'm going to solve that for V12, and I expect a positive answer. Okay, let's see what I get. I didn't read the second part of the question. I need to include a little bit about that into my Y. At 1.75 meters per second. That'd be part A. Then I need to go good. I need to go back up here. Oh, I said, but kinetic energy is not. I might even, let's see. I'm going to predict the KE will be reduced. That's what I think is happening. So, I do need my equation for kinetic energy now. I'll grab that. It's that in. Alright, so it asked me in the second part, how much does the kinetic energy of the system decrease? Make sure I got that right. And so I'm looking for delta KE. And as in with any change, right? Changes are always handled the exact same way. We'll have delta KE equals final minus initial, right? They're always set up that way. In our case, this is going to be the KE of object 1, 2, and that'll be minus the combined kinetic energies of object 1 and object, or car 2, car 1 and car 2. Right? Because those combined are the energy it has before you. So now it's really just, let's substitute everything in. You have 1/2 m12 speed of 1/2 squared minus. Now, do you want me to leave that second part in the parentheses or take it out? What's easier for you guys to kind of see? Keep it in? Okay. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And now just substitute in your values. And crank it out, and you should get, well, it's going down, so you should get a negative answer, right? So give it a try, see what you come up with. And I'll give it a try also. So make sure that on that note, because it asks how much it's decreasing, it doesn't need a negative sign. All right, so on number 4, we've got the two rollerbladers facing each other and standing at rest on a flat parking lot. Why would we put them on rollerblades? What do we want to say about them?
Frictionless?
Frictionless, yeah. So we're saying, hey, just worry about these two things. These two people, don't worry about anything else. And then they push off each other. Now, it doesn't seem like it, but how would you categorize this collision? What would you call it? I'll give you a hint. It begins with an E. Close. The other E one. If you want a hint? Boom! Explosion. Yeah, explosion. Sorry. I'm not sure about this one. I don't know what it is. Yeah, so this is technically an explosion because you have one body, they're together, and then they push off each other, and they're an explosion. So I'm going to write about that. It would be good. 24 would be better. And so this is an explosion. So the momentum is conserved, but the kinetic energy increases. That's about, impulses. They undergo equal but opposite impulses. Yeah. Alright, so now, drawing skill. Okay, so now I've got to draw a rollerblader. There you go. Don't worry if you can't do as well. And then a second rollerblader. And I'm just labeling that so no one thinks I forgot about it. What were their names?
Tracy and Jonas.
I'm just going to label this TJ. Tracy and Jonas. And then afterwards, momentum Tracy. Momentum Jonas. And I could even get, if I wanted to, if I didn't feel like writing stuff, I could have shown that in here, you could have had an impulse on Tracy in that direction, and an equal impulse on Jonas in that direction, if you wanted to show that. You know, if you wanted to draw it rather than write about it. Which way should we call positive? To the right? Is everyone good at that? Okay. And let's see what they told us. Okay, so they told us the speed, so they didn't attach each one. But we need to keep in mind that momentum is a vector. So when we're doing this, we need to keep those directions in mind. So I'm going to, I'll grab my equation in a minute, but the momentum of Tracy Jonas equals the momentum, and that's a vector, the momentum of Tracy plus the momentum of Jonas. And again, I didn't really use before and after because there were one object and then there were two afterwards. So I think my variable notation is clear that they're different things. Let's grab that momentum again. Whoops. Go too high. Alright. So we said to the right is positive, right? And we have Tracy moving to the right afterwards. So that means Tracy's going to have a positive momentum and Jonas is going to have a negative momentum. Because my momentum beforehand is 0. So I can just say 0 equals mass of Tracy, velocity of Tracy, and since I'm still in terms of a vector, my positive and negative haven't come into my equation yet. Oops. Yes. So, 32 for Tracy, 45, and 0.8 for Jonas. Okay. So, 0 equals Tracy. That was enough thing in my head. 32 kilograms. Don't know what that is. 45 kilograms. And negative 0.8 meters per second, because putting in for the velocity, I need that sign. And then just solve it from there. All right, so we're looking at number 10 now. The curling stones, they're made of granite. They have a pretty good elastic collision. Good enough that we can consider it elastic for this, for us. All right? So we've got one moving north, we have the other one resting, and then they collide dead center. So there's no angles or anything to worry about. We'll worry about that in a couple of units. And then they ask for what's the final velocity of stone 2 and the final velocity of stone 1. So let's do a little diagram. I think I'm going to write here that this is an elastic collision. So both momentum and KE are conserved. The stones undergo equal and opposite impulses. All right. All right. So beforehand, I have chugs. How did we name these? 1 and 2. Stone 1, stone 2. Okay. Everyone okay if we take to the right to be north? That's not going to freak anybody out? Okay. So I'm actually going to make that little note in my diagram that that direction is north, and I'm going to call that direction positive. So I know that makes you guys happy. All right. So we've got stone number 1, and it has momentum 1 before. And then we have stone number 2, and stone number 2 has momentum before equal to 0. Right? Good. And then afterwards, we've got stone number 1 and we've got stone number 2. I'm going to predict that stone number 2 afterwards is going to be moving north. And do they have, how are their masses? Let's look at it. So 21, 16. So a heavier thing is hitting a lighter thing in an elastic collision. I think the heavier thing is going to keep moving forward. Okay? If it was lighter or the same mass, I would think it might bounce off. But I think because it's heavier, it's going to keep moving forward. And so that'd be a momentum of 1 after. So that's what I'm predicting. I could be wrong. If I'm wrong, I'll just get some weird signs, things like that. Good? Okay. So that diagram actually gives me my starting equation. That momentum 1 before plus momentum 2 before, both those being vectors, equals momentum 1 after plus momentum 2 after. And then because it's elastic, I know that kinetic energy 1 before plus kinetic energy 2 before equals kinetic energy 1 after plus kinetic energy 2 after. Remember, no vector signs on kinetic energy because it's a scalar. So the direction matters on the blue, on the momentum, but not on the green. All right. I need my equations. I think I'll go back one page and grab them rather than... Oops, I do this. Copy. Paste. So now I'm down to filling in with variables. So I've got the mass of 1, velocity of 1 before, plus, what was the momentum of 2 before the collision? 0. It wasn't moving. 0. That makes life easier. Then mass of 1, velocity of 1 after, plus mass of 2, velocity of 2 after. Both those I left as positives based on my prediction. All right? And I should probably get rid of the vector symbol here. Similar down here in the kinetic energy, 1/2, mass 1, speed of 1 squared, plus 0, equals 1/2, mass of 1, speed of 1 after, squared, plus 1/2, mass of 2, velocity of 2 after, squared. Now, we know the mass of 1. We know the velocity of 1 before. We know the mass of 1. We don't know velocity of 1 after. We know the mass of 2. Similarly, we mark the same things that we know in here. We have 2 unknowns in each of those 2 equations, which means we need to put in our values and then solve them simultaneously. So you got to either use your algebra skills or run out to Wolfram, put them in with you know, like rather than V1A, maybe you use the variable A there. Rather than V2A, you use the variable B there. Something like that. All right. Put them both in there, separated by a comma, or your favorite math solver, and the answers will fall out. You should get 2 positive answers. If you get anything negative, double check you put them in correctly. If they're still negative, and if you did all that correctly, then maybe our prediction's wrong, and maybe the first stone does bounce off. The second stone is gonna go north, no matter what. First stone could bounce off. So this is where you use Wolfram or your algebra skills. All right.